Alrighty, welcome everyone. My name is John Stoltz, and I, along with Amit Pandir and Yunkin Liu, will be covering Linaro Consumer Group's lightning talks. Just a quick agenda. We only have about 25 minutes, so we're going to be kind of going quickly. I'm going to cover the recent developments on Aosp dev boards. Amit will be talking about the Android boot image v3 support on the Dragonboard 845, as well as updates on form factor devices. And then Yunkin will be talking about integrating Docker into Lava testing. All right, so starting off on Aosp dev board updates. So first of all, why do we put all this effort on Aosp dev boards? Well, these boards are very valuable testing platforms that allow us to test a large number of kernels with the very latest Aosp userland. We basically are working against Android 4.14 all the way through Android mainline, doing regular testing, basically ensuring that as the LTS updates land in those trees, we don't see any regressions, so that vendors can be more confident when they're deploying those updates to their products in the field. Additionally, we do regular testing of Aosp with Linus's upstream tree, and we do find a number of regressions regularly. In the most recent merge window, we actually caught two block device issues where basically I guess encrypted partitions and dynamic partitions both failed at boot. And we were able to quickly bisect these down, provide that feedback to the maintainers, get those things fixed before even RC1 was released. And so this was really nice to be able to kind of find and solve these things before they were affecting really anyone. But outside of testing, I think these boards are really useful as development vehicles. And for example, they've been used. We've used them for GKI prototyping in the early days, and basically helped really validate that the approach that GKI was using was going to work across different vendor SoCs. Additionally, we use these heavily in the recent work transitioning from Ion to DMA buff heaps. But I think what's most important is that because these devices can run mainline kernels, we can do a lot of our development or Android-focused development against those mainline kernels and be able to submit those changes confidently upstream. And this moves Android development sort of into a more upstream-first approach where we're able to kind of get the work done upstream, get the code merged, and then backport patches rather than kind of working against an old tree and then creating that technical debt that has to be carried forward. So on to the specific boards, the Dragonboard 845 or RB3, as well as the Heike 960 are the two boards that we are actively working on. We've recently on both boards, we've gotten the Android 12 5.10 kernel support in place. Also, both of the boards boot with GKI v2, and so we're doing regular GKI testing, as well as the KABI upkeep, which in the days before the KABI is kind of locked down can be significant. On the Dragonboard 845, also thanks to the Qualcomm landing team, we have full functionality upstream on the board as of 5.11. Additionally, the GKI module enablement has mostly gotten upstream. Aboot image v3 support, which Amit will cover later, has landed as well for the board. Amit's also enabled proper VirdAB support for the device, and Amit also recently, because the board has open graphics, he's updated Mesa to 20.3.4, I believe, and that was as of up until the last couple of days was the latest. So. Also, while the board has open graphics, it also has open video decoding. So we're really excited to try to get the v4L2 integration in Aosp working. And so that's something that we're putting a lot of attention on right now. Additionally, the mini GBM Gralloc is something that we're hoping to switch to in order to align with both the Cuttlefish and Chrome OS usage. And then Buddha's recovery and fast boot D support is something we're looking at enabling in order to improve GKI testing. And then finally, the last few GKI module enablement patches, we want to make sure those get upstream. Over on the Heike 960, other than the topics I've already covered, the USB functionality has gotten upstream recently. We have a couple small fixes for reliability that are still pending, but out of the box, it should just work. And then also dynamic partitions and VirdAB support have both been enabled on the board to bring it kind of more in line with modern devices. As far as work in progress, the system uncached heap is something we are working on pushing upstream, and we want to enable in the Heike 960 Gralloc because that provides a nice performance improvement. And unfortunately, we still have quite a bit of out-of-tree code, the display driver and the audio driver. And so trying to get any of those upstream would be nice as well. Now, there's still work going on to enable additional boards in Aosp, but unfortunately, we can't talk about that just yet. So do watch this space. We'll be excited to share that as soon as we can. And with that, I'm going to pass it on to Amit.
Thank you, John. Hi, this is Amit. I'll start with a quick update on the boot image header version 3 support, which we have recently added for Dragon Board 845C. Next slide, please. So a quick background on version 3 header. In version 3, vendor-specific information is factored out of the traditional boot image and moved into a new vendor boot image. So now we have a generic or vendor-neutral boot.img and a vendor-specific vendor_boot.img. Boot image only contains generic components like the kernel image and a RAM disk with GKI kernel modules. The vendor boot image, which is loaded from a new vendor boot partition now, contains vendor device tree blob, a vendor RAM disk with platform-specific kernel modules, and platform-specific information like page size, load addresses, kernel command line, etc. Version 3 header is a requirement for GKI compatibility and therefore must for Android devices launching with 5.4 or newer kernels. Next slide, please. Just like the older boot version formats, bootloader does most of the heavy lifting here. It concatenates the two RAM disk CPIO archives, and the resulting overlaid CPU archive will be used as a initramfs during boot. Both the RAM disks must be compressed in the same format for the concatenation to work, and must be LZ4 compressed for GKI compliance. For Dragon Board 845C, we were able to reuse Code Aurora's boot image version 3 implementation. Many thanks to Mayank Grover, who has helped us debug the bring-up issues due to page size mismatch. And recently, Android boot image header version 4 is also spotted in Aosp. Version 4 supports packaging multiple vendor RAM disks in vendor boot image and let the bootloader select one or more RAM disks to load at the boot time. This is similar to how vendors pack multiple device tree blobs in dtb.img. Next slide, please. Next up on today's agenda is the status update on running mainline kernel and Aosp on form factor devices. Next slide, please. So running mainline on form factor devices. We have been chasing this topic for a long time. And please check out our previous presentations and blogs for the rationale and our previous efforts. The key takeaways are that it helps us avoid development board functionality gap between development and testing. It also helps us validate and compare upstream solutions with downstream vendor solutions. Next slide, please. As of version 5.12 RC2, we have basic features like Wi-Fi, Bluetooth, audio, touchscreen, etc. working. Running mainline kernel on Poco F1 phone is a community-driven project. We are collaborating with a number of different groups, and it's really a community effort that we are really appreciative of. A special shout out to Linaro's Qualcomm lending team, Post-Market OS and So Mainline guys, and Mesa developers for helping us debug and enable new features. Next slide, please. There's a decent progress on upstreaming Poco F1 features as well. Bluetooth just works straight out of the main line. Display panel and lab IBB regulators are already upstreamed. Only DTS patches are remaining. Wi-Fi and backlight drivers need a small workaround to get them to working. GPI DMA driver got upstreamed recently, but I2C and SPI user support is currently under review. We need this patch set for touchscreen and audio amplifiers to work. SDM845 sound card and codecs is already upstreamed as well, and only DTS patches are remaining. Touchscreen driver is upon LKML for review. Also, these are the patches or features which I actively use and track in our builds. And there may be many more relevant drivers and fixes which are either already upstreamed or are in progress, and which I may not be aware of. And as you can see, we have got contributions from not just from Linaro or from but a specific company. You can see a true community collaboration here, which we really appreciate as a mainline Poco F1 user. Next slide, please. Speaking of in-progress features, there are a few exciting features currently under progress. Andrew is working on getting QRTR modem support enabled in Modem Manager for mobile broadband connectivity to work. Joel from Postmarket OS is working on a fuel gauge driver. It is still a work in progress, but basic features like battery charge, health status, temperature, and charger hot plug detection is already working. Celeb, again from Postmarket OS, is working on the haptics driver. And then there's a to-do list for interested Linux Aosp developers to join in. Do check out the README page for instructions and how to get started. That is all from my side. Over to Yonkin for how to use Docker for Lava Android test setup.
Hello, everyone. I'm Yuqin Liu from the Linaro Consumer Group. Here, I will give one short introduction about enabling the Docker method for the Android testing. Next slide. About the Docker method, Antonio had talked about it before. You could check the session for the details by following the link. For us, we could test locally with the exact same host environment as on the Lava side by using the same Docker image. This will help us for failure reproducing. And it is possible for us to maintain the Docker image out of the Lava framework by ourselves. This will help to reduce the request to the Lava team and the lab team for trivial failures, which we often have with our XC method. To enable the Docker method with the Lava jobs, we need to prepare the Docker image and upload them to the Docker Hub site first. Here are the links which you could refer to for the instructions, and the links to the Docker file and the Docker image we use for our test. We also need to update the job templates, which are used to generate the job definitions. Most of the necessary changes are described in the Lava document here. You could refer to. For us, we need to have two deploy actions. One is for the downloads, and another one is for the fast boot deployment, as we need to use the boot image file in the test actions after the deployment. We have enabled the Docker method for some projects of the for the high-key, high-key960 and the DB845 both, but there are still two major issues under discussion with the Lava team. First one is with the TI-X15 board, which will deploy the same image file to two different slot partitions. And another one is about running the dmessage command inside the Docker container, which will be helpful for the debugging purpose. Okay, that's all from me. Thank you.
Alrighty, I think that's it for us. Thanks so much, and I guess we'll go to live questions now. All right, thank you.